This video is going to go over molarity and dilutions, and then at the very end we're going to do some practice problems, and that's going to lead into some practice on solution stoichiometry. We'll start with making a solution. So here we have a volumetric flask that has a nominal volume of 250 milliliters, which means if you dilute it to the line on the neck, then the volume contained inside would be 250.00, probably milliliters. They are very precise and accurate kinds of glassware. So we have a yellow solute that's a solid, and we've measured out some mass that we can convert into moles. And we're going to add that to the flask. Add some sort of solvent, possibly water, and we're going to swirl it around until that solute dissolves in the water to form a solution. And then we're going to, once it's fully dissolved, we're going to dilute with water or the other, whatever solvent we're using, up to the line on the neck. We're going to make sure that the meniscus, the bottom of the meniscus lies flat on that line. And if we wanted to determine the molarity of this solution, we would know the mass that we added in, and we could convert that into moles. Molarity here would be calculated using the moles of solute, that's the yellow solid that we added, divided by the volume in liters of the overall solution that we created. And so in this case, the volume of the solution is 250.00 milliliters, and so in liters that would be 0.25000 liters. We're going to do some calculations at the end that will hopefully explain all of this. Now, another common calculation or thing you might have to do in lab is a dilution. So in this case, we have a stock solution that is a more concentrated solution, and we want to dilute it and add some solvent to it to make it less concentrated or more dilute. So we're going to take some volume out, and we're going to put that in a flask that would contain a larger volume once we dilute it. We're going to transfer some of that over. This looks like it's probably maybe a 10 ml volumetric pipette, although I don't really know if they dispensed the whole 10 milliliters, but let's just say they did. So they took, let's say, 10 milliliters of a stock solution, which is sort of a dark green color in this case, and they added it to a 100 ml volumetric flask. So the nominal volume on this flask is 100 milliliters. So if you dilute to the mark on the line, you can see the line on this neck in the picture actually, and it's at about the, behind it is the pipette. So it lies about parallel with the, I don't know, 8.35 line or so. You can see the line on the flask there. But then if you add solvent to the flask and shake it up really well, and then you dilute it to the line, you can see the bottom of the meniscus lies flat on that line. And you can see that this green solution is a much lighter green color, and that's because this solvent doesn't have color. We've diluted the solute to make a more dilute, less concentrated solution. Now if we wanted to calculate the concentration of this solution, all we would need to know is the initial concentration of the stock solution, the volume of that stock solution that we added, and the final volume of our finished solution, which is 100.00 milliliters. So dilution calculations conceptually are not very difficult to understand. Here, if you see, our solute is these orange, represented by these orange spheres, or reddish, whatever color you think that is. And then the solvent is sort of that kind of light gray, clearish looking liquid. The idea here is that we're trying to calculate the molarity of just the solute in our solution. And so you can see that dilution does not involve the addition of any additional solute. It's just addition of solvent. And so it just changes the volume of the solution. It does not change the moles of solute. And so you can see that there are 5 sort of reddish orange spheres on the left, and there should still be the same number of solute spheres on the right because we haven't added any solute. We've only added solvent in order to dilute it. So molarity times volume of this solution on the left-hand side, that should give us moles of solute, because molarity is moles per liter. We multiply by the volume in liters. That should give us moles. So the moles of solute on the left should equal the moles of solute on the right. So our next, on the right-hand side, whatever molarity that is, times the volume of that solution, those should equal each other. So this M1V1 equals M2V2 equation is something that you will use to calculate concentrations when you perform a dilution. We're going to do a couple of different calculations as examples. So the first one is really just a series of calculations involving calculating the molarity of a solution. And then there's a dilution, and then you're mixing two solutions together. And this next problem relates more to solution stoichiometry. And so we're going to do these one at a time. So we have a set of problems here. We're going to make a solution of cobalt chloride by dissolving a mass of cobalt chloride in enough water to make 425 milliliters of solution. I'm going to calculate the molarity of cobalt chloride. Molarity, remember, is, so here I've written molarity, capital M is the abbreviation for molarity, and the subscript here is cobalt chloride. That equals moles of cobalt chloride, that's my solute, divided by the overall volume of this solution in liters. So to get moles, abbreviation for moles is lowercase n, so moles of cobalt chloride. If we want to calculate that, we take the mass of cobalt chloride, and we need to divide by the molecular weight. Molecular weight is going to be cobalt, 58.93 plus 35.45 times 2, and that gives me 129.83 grams per mole. So if we divide the mass by that molecular weight, we get 0.04968 moles, and that goes in the numerator. The denominator is 425 milliliters, which converts, if you convert this into liters, you can either divide by 1,000 or you can move the decimal point over three values, three spaces, and that gives you 0.4250 liters, and that goes in the denominator. And then our answer is 0.11688949, which is going to round to 3 significant digits because of the 6.45 grams gives us 3 sig figs. So 0.117 molar, I'm going to circle that. Now part B is a dilution problem. We're going to dilute 10 milliliters of the solution we made in A, and we're going to dilute it to 100 milliliters with water. So we're going to use this equation, M1V1 equals M2V2. So in this case, M1 is the answer to part A. I'm going to use the unrounded number. I'm taking 10 milliliters of that solution, so 10.0 is V1, equals M2 is the number we're solving for, and 100.0 milliliters is V2. Now in this case, I don't have to convert from milliliters to liters whenever you're using this dilution equation, M1V1 equals M2V2. As long as you're using the same unit for volume, you can just use milliliters or liters or microliters or whatever you're given. So here M2 is going to be equal to 10 times 0.1168949 divided by 100. And that's going to give me 0.01168949. Here I'm just saying that milliliters cancel. As long as you use the same volume units, you don't have to convert to liters. 0.0117 molar. Now this is a special kind of dilution. We're taking 10 mils and we're diluting it to 100 mils. So this is what we would call a tenfold dilution. Tenfold dilutions, you can determine the new molarity as long as all you know is that it's a tenfold dilution. And so if you're diluting something tenfold, that means that the new molarity will be 10 times less than the old molarity. So you're just going to take the old molarity and divide by 10. That's what it's showing you here. And you do need to know that for a tenfold dilution, if you're given nothing else in the problem, I do expect you to know that with a tenfold dilution that you divide the molarity by 10 to get the new molarity. Part C, we're going to take 10 grams of the sodium chloride, 10 grams of sodium chloride to 25 milliliters of the cobalt chloride solution described above. This is a little bit vague. I probably should have written described in part B above, but I didn't because we have two different cobalt chloride solutions, and I don't really know which one I meant to use, but I should have been more descriptive here, and I was not. So let's assume that it's the one in part B. and we're going to dilute that mixture to 40 mils with water. Let's make sure everybody knows what we're doing here. We're going to ultimately calculate the molarity of chloride ion in the resulting mixture, which is a little bit complicated, but I want to make sure everybody understands. So this is the answer to part B. So I'm going to take my flask and I'm going to put in some amount of solid sodium chloride, 10 grams. And then I'm going to take my solution that I made in part B and I'm going to add 25 mils of that to the same mixture. I'm going to mix them together and then I'm going to dilute it to 40 mils with water. So I'm going to dilute up to, let's assume that this is a 40 ml flask, which probably doesn't exist, and dilute to the line. So I'm ultimately trying to calculate the molarity of chloride ion, which is what this says here. Capital M is molarity, chloride ion is the subscript. So the molarity of chloride ion is going to be moles of chloride divided by the total volume of the solution in liters. So the issue here is that we have chloride ion coming from two different sources. We have chloride ion coming from sodium chloride, and we have chloride ion coming from cobalt chloride. That's what this is telling you over here. So you have to figure out how many moles of chloride come from each source and add them together for the numerator. So we have 10 grams of sodium chloride. We convert that into moles. 1 mole of sodium chloride for every 1 mole of chloride ion means I have 0.17115674 moles of chloride. Cobalt chloride is going to contribute some as well. So we're going to take my molarity that I calculated, 0.011689 moles per liter, and I'm going to multiply by the volume that I'm adding. That should make liters cancel. And then I'm going to end up getting, and then I need to multiply because there's 2 moles of chloride ion for every 1 mole of cobalt chloride. That means I need to multiply by 2 to get moles of chloride. And that's going to give me 0.000584475 moles of chloride from the second source. And we're going to add those two together. 0.1711 plus 0.000584. And that's going to go in my numerator, 0.1717 moles of chloride. My denominator is just the volume of the solution. The overall volume is 40 milliliters, which I just need to convert into liters. So 40 mils is here. I'm going to convert that into liters. And that's 0.0400 liters. So my final answer is 4.2925. And then for significant figure purposes, my 10 grams of sodium chloride has 3 sig figs, which means this 0.171 number has 3 significant figures. It's accurate to the thousandths place here, 3 digits after the decimal. This number of moles, remember, originally came from the 10 grams, this number here came from 10 grams. And then this number, as the second number, that one's accurate to 3 digits after the decimal because that came from the 0.0117 number. That was the molarity from part B. And that also has 3 sig figs. And so here we have a number with 3 digits after the decimal. This number has 1, 2, 3, 4, 5, 6 digits after the decimal. When you add them together, the answer should only have 3 digits after the decimal. It's the less accurate number that you round it to. So the sum here is only accurate to this thousandths place, which is here. And this number, the denominator, has 3 sig figs. The numerator has 3 sig figs. So my answer should have 3 sig figs. So that should be 4.29 molar. And we're going to circle that as our answer. Now we're going to move on, do one more set of problems. We make a solution of iron 3 nitrate. And we're going to describe how we make it, 14.5 grams of solid iron nitrate in 200 milliliters of solution. What is the molarity? So this is straightforward. It's just like the last one. We calculate moles of iron nitrate using the mass. Molecular weight, we add iron, 55.85, plus 14.01 is nitrogen, and oxygen is 16. So remember, when you do the molecular weight here, you have 1 iron, you have 3 nitrogens, and you have 9 oxygens. So make sure that you calculate the molecular weight correctly. Grams cancel, and you end up with moles. We have 200 milliliters overall of solution, which is 0.2000 liters. So the molarity of iron nitrate is 0.2997. Significant figures, we start with 14.5 grams, which has 3 sig figs, which means my numerator should have 3. My denominator should have 4, which means my answer should have 3.300 molar. If we move on to part B, we dilute 40 milliliters of that solution that we just made, just calculated. We dilute it to 300 milliliters with water. We dilute 40 mils to 300 mils. What is the molarity of this solution? So again, we're going to use M1 V1 equals M2 V2. We're going to plug the numbers in. M1 is this unrounded 0.299735406 number that I'm going to put up here. V1 is 40 milliliters. M2 is what we're solving for, and V2 is 300 milliliters. And that's going to give us 0.0399647 molar, which I'm going to round to 3 sig figs again, 0.0400 molar. And it's always good to verify that we get a number that's smaller than the original number, and that should be true because this is a dilution problem. So this should be more dilute than the original solution. You mix the aqueous iron 3 nitrate made in part B with aqueous potassium sulfate. These react to form iron 3 sulfate and aqueous potassium nitrate. If 10 milliliters of the iron 3 nitrate solution from part B is mixed with 42 milliliters of potassium sulfate, how many grams of solid iron 3 sulfate will form, assuming that the yield is 100%? Now, this is what we call a solution stoichiometry problem. Okay, so here it's the same stoichiometry you learned in the last chapter, but we're adding in molarity to the different toolboxes, the different tools in your tool chest that you can use. So I want to have a little side note here about solution stoichiometry. In all the flowcharts that we've been using from the textbook, we always have this generic reaction, with lowercase letters being the stoichiometric coefficients and the uppercase letters being the reaction components. So this is my generic reaction. If I have grams of A, and in previous flowcharts we've had mass of A converted to moles of A using molecular weight of A, and then we use the reaction stoichiometry to convert from moles of A. In this case, we're converting to moles of C. And then we can convert from moles of C back to grams of C using the molecular weight of C. And of course we can go from moles of A to moles of B, or we can go from moles of A to moles of D, or we can go from moles of C to moles of D. We can convert between any of these that we want. Once we have moles of any reaction component, we can convert to moles of a different reaction component, whichever one we want. And then using the respective masses of those molecules, whatever the reaction component is, A, B, C, or D, we can convert back to grams for any of them. Now, solution stoichiometry just adds a new way of getting to moles. Okay, so instead of going from grams of A to moles of A, let's say A is a solution. Let's say that you have component A, and instead of knowing the mass, you know the molarity and the volume. If you know the molarity, which is moles per liter, and you know the volume in liters, all you have to do is multiply those together to get moles. Now that might be true on the other end as well. It might ask you, what is the molarity, knowing the volume and the moles that you create? So this problem has both examples of those. So we're going to start with 10 milliliters. We know the volume, and we know the answer to part B. So we know molarity and volume. We're going to convert milliliters into liters, and we're going to multiply that by the molarity that we calculated in part B. And so that means we have that many moles of iron nitrate. We're going to take the same approach, 42 milliliters and 0.012 molar. You need to convert milliliters into liters, and then you multiply it by the molarity, and that should give you moles of potassium sulfate. Next, we need to, since we're given moles of both reactants, we need to identify which one is the limiting reactant. So we know the stoichiometry, if we calculate how many grams of solid iron sulfate form, and we just pick the lower number, we need to figure out which one is the limiting reactant in order to answer the question. And we don't know the answer to that. That's why I wrote limiting reactant question mark, because we don't know which one it is. So if we start with moles of the first reactant, and then we take the stoichiometry, which is 2 to 1. So I'm taking the answer to the first calculation up here, 0.000399647 moles of iron nitrate. I'm converting that into moles of product, iron sulfate. because ultimately I want to figure out what mass of iron sulfate forms, but I don't know if this is limiting reactant or not. So we're going to start with this reactant, divide by 2, and that's going to give me 0.000199.8 moles. If we take the other reactant and divide by 3, we get 0.000168 moles. So since we have moles of the product here, you don't have to go all the way to grams. You can compare the two mole quantities. As long as they're moles of the same thing, which these are, then if iron nitrate is a limiting reactant, then we're going to form 0.000199.8 moles of product. If potassium sulfate is the limiting reactant, we're going to form 0.000168 moles of product. So you always pick the lower amount, that's the second one here, 0.000168, which means that potassium sulfate must be my limiting reactant. So we've got to pick the lower amount, and we're going to convert that into grams because it asks for grams. That means potassium sulfate is the limiting reactant and iron nitrate is the excess reactant. We're going to convert moles into grams here. In this problem, we have 2 atoms of iron, 3 atoms of sulfur, and 12 atoms of oxygen, given molecular weight of 399.91 grams per mole. We multiply moles by the molecular weight to get 0.067184888 grams. We're going to round to probably 3 significant figures. Oh, it looks like, it looks like it's going to be 2 significant figures. 42.0 mils has 3 sig figs, but 0.012 molar only has 2. And so these are the 2 numbers used in this calculation, which means that the number of moles of potassium sulfate is only accurate to 2 significant figures, just this underlined 0 here, which means that we need to round this to the thousandths place to 2 sig figs, 0.067 grams. Now the last part of the question, there's one more part of the question. What is the molarity of potassium nitrate in the resulting mixture? So we also end up with a second product, potassium nitrate, which is aqueous. The first one is a solid, so it's kind of appropriate to ask what mass forms. But for the potassium nitrate, the question is what is the molarity of that product that forms? And so this is a separate sort of question. We're just going to figure out how many moles form and divide by the volume. So molarity is moles per liter. So we can figure out how many moles form. You have to use the limiting reactant here. And so we have our limiting reactant, moles of our limiting reactant are here, 0.000504 moles of potassium sulfate. We're going to convert that into moles of product. The stoichiometry is 3 to 6. So 3 moles of potassium sulfate will form 6 moles of potassium nitrate. And so that means that we're going to multiply this number ultimately by 2, and that's going to give us 0.001008 moles of product. And we're going to divide by the total volume, which appears to be 10 milliliters plus 42 milliliters, is going to give us 52 milliliters. 0.052 liters, which gives us 0.01938 molar. It appears that we are again going to need 2 sig figs. 0.019 molar is the final answer.